Okay, good afternoon, everyone. The homework, some of you haven't finished, right? So I'll give you until tonight for the density. So today we're going to look at the next chapter, force pressure. Okay. And after this, if you have any problem with the homework, we'll discuss the question later. Okay, now let's recap from the beginning, forces and pressure. So first we look at the concept of a net force. What is a net force? Net force is a combined effect. Write this down. Combined effect of forces. Meaning that when you have more than one force acting on a single body, then you can replace all the forces into one single force. You combine everything into one single force. That is called the net force. Okay, so looking at this diagram, 5 Newton, if I push down with 5 Newton of force and somebody push up with the same amount of force, then these forces will cancel out each other. This one will cancel out with this one. Okay, now notice that when I analyze the force, I have to make sure that the forces, they are in the same line. This is straight, vertical forces. This is also vertical forces. So they are in the same line. I can add them. I can minus or I can add them. This is vertical force, but this one is flat, right? It's horizontal. They are not in the same line, so I cannot add them. Okay, now the top one, 5 Newton, cancel out by the bottom force. And then we look at these two forces, 8 Newton and 3 Newton. If I push it to the right with an 8 Newton force, somebody push it with 3 Newton, then my force becomes less, right? 8 Newton still to the right because my force is bigger. Object would still move to the right, but with a less force, 5 Newton. So we take the difference. Yes, 5. Okay. Now, so the rule of thumb is if the forces, they are pointing at the same direction, you add them. If they are pointing at opposite direction, you minus them. Okay. So this one, I can redraw my diagram and then I get rid of all the forces. I just put one forces here, 5 Newton to the right. Put the direction, you can say right, or you can say east. Okay. Always label the value with the direction because force is what we call as a vector. What does a vector mean? A vector means that it has a direction. When I say 5 Newton, the next question you ask is, okay, where is it acting? 5 Newton, is it pushing up? Is it pushing down? Is it pushing left or right? Because the information is not complete, right? So it has to comes with a direction. Is it 5 Newton? Up or down? So that the information is complete. Okay. Now, this diagram is the same as this diagram. Okay, it's the same, it has the same effect. So I have to make sure that when I find the net force, it has the same combined effect. Now, second, consider that a body is falling through air. It's falling due to its weight, pulling it down, and then there's a drag. Drag comes from the air resistance. So the air tries to slow it down. Okay, now analyze the force. Is it in the same line? Okay, same line, so I can add it up. Do I add or do I minus? you see the direction is opposite, right? If I pull it down with 50 Newton, and it wants to go here for 12 Newton, the net effect would be still downward, minus it, 50 minus 12, so it's 38 Newton down. 38 Newton down, so redraw your diagram. I replace the two forces with only one. Okay, the way you draw the force, I always start from the center, because we are taking the center of mass. Okay, we are assuming that all mass come from the center. So 38 Newton downward. And this diagram is the same as this one. Number 3, this one you have many forces, right, coming in all directions. So you just look at the same line. Okay, 3 and 5, 5 and 3. Simplify them. Okay, upward forces, I got 2. 5 Newton going up and 3 Newton going up. So I have total of 8 Newton going up and total of 8 Newton also going down. Okay, 3 and 5 going down. So this one will cancel out with this one. Okay, yes, correct. So you have 2 Newton to the left, because this one add up 6 and then minus the 8. So this one I can write it as, redraw the diagram, and I replace it with one single force, 2 Newton here. The last one, push. I push it with 25 Newton, and there's a friction with the surface, 8 Newton. Where is it going? It's still going to the right, but my force has become less. 17, right? 17 Newton to the right. What are all these forces? This one, 5 Newton, 38 Newton, 2 Newton, and 17 Newton. This single force, we call it the net, because it is the net result of all forces. Or other terms, we can call it the result, the resultant force. Resultant force. Net force and resultant force, they are the same thing, just different terms. Okay, same meaning, same thing. How many types of forces are there? Okay, there are 2 main classification: contact forces and non-contact forces. Contact forces requires direct contact, as the name suggests, right? Direct contact. So 2 bodies, they are indirect contact. Non-contact means no contact. Examples: contact forces like friction. Frictional forces. Friction can comes in different forms with surface. Okay, for example, like this one, the last example here, a rough surface, or it can be friction with air, like the drag. Okay, that is also considered friction with air. Or it could be friction with water. An object moving in water, there's a friction with water. Okay, or we call water resistance. Okay. Now, other than friction force, what else? We have push or pull. Okay, normal, common push or pull forces. How about non-contact forces? Non-contact forces is the field forces, like gravitational field. Okay, now what is the meaning of field? If I say that it is a field force, understand the concept of a field force. You see, I place this object in space. Okay, and then I observe the movement of this object. If it is not moving, then there is no force acting on the object. And then if it's moving, let's say it's moving like this, from here to here, If it's moving means that there's force acting on it, right? But where does the force come from? Because there's no object touching it. Okay, there's no object touching it. So I place it in this space, but it is moving. So from this observation, I will conclude that this thing is being placed in a force field, in a field. Okay, what field? It could be gravitational field, it could be magnetic field, it could be electric field. Not only gravitational, there are many, many different types of field. Okay, so now maybe you'll ask, okay, whose field is this? Whose field is this? Maybe it's from the nearby planet, Earth. This is the field of Earth. So this field is acting a force on the object without contacting it, right? Without touching it. And the force that we can say that the force, who is acting the force? The force is acted by the Earth. Okay, the force is acted by the Earth. Whose field is this? The Earth's gravitational field. So the force created here is the Earth's force. It's acted by the Earth. Okay, just like a spider web, just like a spider. You can see the spider, right? But you cannot see the spider web. It's invisible. So the spider web is like the field. When the insect gets caught up in the spider web, what happened? The spider manipulates its web and then it pulls the insect towards it. Okay, it's the same concept. For any field forces, okay, without needing direct contact. Okay, so that is gravitational field, and then we have magnetic, right? Magnetic field. The Earth, not only it has gravitational field, it also has magnetic field. Where does the magnetic field come from? Because the center of the Earth is made of iron. The Earth core is made of iron. So iron is a magnetic material. So it has a magnetic field. What does it do? It protects us from the sun, the radiation, the UV ray, all kinds of radiations. Okay. Now, other than these two, we have electric field. Electric field comes from a charge. How many charges are there? You learn about positive charge. We have negative charge, two types of charges, right? So positive charge has its field. If you place another positive charge in this field, these two will repel each other, right? Because there's a force created by this field, and this field is electric field. It is not the same as gravitational field. Okay, so now know the types, okay, this type, and to be able to differentiate it. Okay, the next one, we are going to look into more detail, the field forces. Okay, let me just take this. I'll screenshot this down. Okay, now look at this one. Non-contact force, gravitational force. Here I got 3 planets, Earth, Mars, Jupiter, and having their own gravitational field. Now there's one physical quantity, gravitational field strength. It is the G, right? The G in the calculation. What is it? How do you define gravitational field strength? We said that the amount of force acting per unit mass. Make it simple, just this sentence. Amount of force acting per unit mass. You can look at the unit to help you. You see, the unit for G is N/kg, right? If you remember the unit, you can kind of find the definition, the meaning of it. For example, you see N/kg means N per 1 kg. This is like Newton per 1 kg. So the amount of Newton, which is force, the amount of force per 1 unit mass, 1 kg is 1 unit mass. Okay, so amount of force acting per unit mass is the gravitational field strength. It is a fixed value for each planet. It does not change. Why it does not change? Because this one, it comes from what? It comes from the mass of the object. The larger the mass, the higher will be the gravitational field strength, or the stronger the field. Okay, the higher the mass, the stronger the field. Earth gravitational field strength is measured at 10 Newton/kg. To be accurate, the actual value is 9.81 Newton/kg, but it's okay to use 10. Okay, it's okay to use that in your calculation. Okay, so meaning that for every kg, it is pulling 10 Newton of force. If you put 3 kg object inside the field of Earth, how many forces acting? 1 kg is 10 Newton, right? For every kg. So if you have 3 kg, then you have a total of 30 Newton pulling it down. Okay, now, one thing also I have to remind you, how do you label the forces in the field? The force, what is this force? This is gravitational force. The way you label it is always pointing to the center of the object. Not always down, no. Always to the center. So meaning that if your object is down here, we don't point it like this, no. Okay, it's towards the center. So it's going like in this direction. This is how we label it, label the forces. Now, if I have 10 kg placed in the field, force is pulling it in this direction. Oops, sorry, let me correct it. Okay, in this direction. So the body will move in this direction, same as the force direction. How much is the force? 10 for every kg, there is 10 Newton. So 10 kg, you times that, 100 Newton is pulling it, this one, down. So in general, I can say that for an object with mass m, with an unknown mass m, there's an amount of gravitational force pulling it, and this force is equals to the amount of the mass times into the gravitational field strength, and that's how you get your W equals to mg formula. Force equals to mg, I can also write it W equals mg. W is the, what is it? Is it work done? No, so not work done, okay? This is weight. Weight, the force is the weight. The force is the weight. Is this the weight? 3 kg. 3 kg is not the weight. Please, 3 kg is not the weight. It is what? It is the mass. 10 kg is the mass. Okay, how do you tell? Look at the unit, kg and Newton. Okay, now, so is weight and mass the same? No, not the same. Weight depends on what? If you look at W equals to mg, weight depends on mass and the g. If the g value changes, your weight is going to change from this equation. If this gets bigger, then the weight gets bigger. But the mass is just mass, it doesn't change. Mass is the amount of substance in your body. Okay, doesn't change. Okay, how, you see, the gravitational field of Earth, how big is this? The gravitational field of Earth is so big because how far is the moon away from the Earth? It's about like 384,000 kilometers. That's the distance of the moon. So meaning that this gravitational field extend outward until 384,000 kilometers. Okay, that's very big. The greater the mass, the bigger the field, or the stronger the field. The sun's gravitational field, it can hold all 8 planets together. okay, because of its mass, a few thousand times greater than the Earth. Okay, now say that I move this object, the 3 kg object. I move this object to Mars. Okay, so it's now at Mars, 3 kg. What is going to be the weight? Okay, first, does the mass change? Does the mass does not change, right? I move it here, it's still 3 kg because the amount of particles does not change. But the weight changes. Here, force acting, we use W equals to mg. So 3 times into the strength of Mars is 3.7. So 3.7. 11.1 Newton. Compare the weight. Here on Earth, the object weighs 30 Newton. On Mars, it weighs 11.1 Newton. So it weighs less. If I move the same object to Jupiter, here, 3 kg, W mg, 3 times 24.7. This one, the G is so huge. How big is Jupiter? Jupiter is made of gas, right? It's a gas giant, but how big is it? Imagine that you take 11 Earth, put it side by side. This is one Earth, this is another Earth. 11 Earth, put it side by side, you get the diameter of the Jupiter. Okay, that is the size of it. That is just the diameter. We haven't looked at the curvature. Okay, the curvature of the Jupiter. Okay, so because of its massive size or its massive mass, it has a higher, much higher gravitational field strength. For every kg, it is 24.7 Newton. So what is the weight of this object on Jupiter? Times 3. Okay, 74.1 Newton. Okay, 74.1 Newton. So now, field, so we understand that field comes from where? Comes from mass, right? The higher the mass, the higher the field. Now, maybe you might be asking, does a person have a field? Because if according to this theory, anything that has mass has a field, then does it mean that a person also has its own mass, right? Does it have a field? Does it have a gravitational force? Okay, the answer is theoretically, yes. Every object with mass has a force of attraction. Okay, but how come we don't feel it? Because our mass is so small compared to the mass of the planets. If you look at the mass of the Earth, how much is the mass of the Earth? It's about like 6 times 10 power of 24 kg. How much is your mass? Your mass is like, for example, like 40 kg. This is just very tiny fraction of it. So you don't feel your own field. You don't feel your own gravitational force of attraction. But theoretically, yes, every human has its certain amount of attraction force. Okay, attraction force. Okay, so in this part, you need to be able to tell the differences between mass and weight. Also, it might come out, the difference between mass and weight. Okay, let's do a table and to see what is the difference between okay, mass, weight. First, you talk about definition. Meaning of mass is the amount of substance. Weight is the size of gravitational force. That's the first one. Second, talk about the unit. Mass has a unit of kg, weight has a unit of Newton. Measurement, how do we measure them? Mass, we can measure using a beam balance. Weight, we can measure using a spring balance. So this is calibrated in Newton. This is calibrated in kg. What else? Talk about the consistency, whether it changed or not. Mass does not change. Does not change. This one, it varies, right? It changes, varies in different locations. Take note of this. Okay, next one. Adriana, is your line okay so far? Okay. Okay, exercises. Try this. We'll give you a few minutes, then we look at the answers. Oh, okay. So there's a correction here. This is supposed to be Q, right? Yeah, this change this to Q. Everybody's like finding where's planet Y. Q. Okay, we'll look at answers in the next meeting.